If you don't know the rules, then you aren't going to be able to answer it. Anybody remember rule number 1? 1 to 9 are always significant. That's not quite fair to have you answer. But it's okay. So our 1 is absolutely significant. Okay? Now we've got an issue. We've got a whole bunch of zeros. Are those significant digits? That's where our other rules come into play. Rule 2 was looking at no decimal point, I think. I don't remember how I've got them numbered. Rule 3 was looking at with decimal points. Which rule should we be looking at? With decimals. What's our rule with decimals for significant digits? A 0 must be preceded by a significant digit for the number to be significant. Right? So we'll go through and take a look at our very first 0. Is there a significant digit in front of that 0? No, which means that 0, not significant. Move to the next 0. Is there a significant digit in front of it? No, which means not significant. Last 0. It does have a significant digit in front of it. That's our 1. That is significant, which means I have a grand total of 2 sig figs. My answer is B. Okay, so it's just following the rules of what makes sig figs. Nope. Nope. Question 2. What do we have to do? Thankfully, we've all got calculators, because I wouldn't be able to add that in my head. We got 11.666 plus 7.77. I lied. Maybe I can't add it in my head.
19.436.
Hey, look at that. Okay, now we have that big long string of numbers, and look at that. The answer choice is there, so we bubble it in. It'd be wrong. Okay, remember, when we're looking at these kind of simple manipulations, they're really asking about significant digits. So you have to evaluate your significant digits appropriately. When you're doing addition and subtraction, how do we determine sig figs? The least accurate decimal place. The least accurate place in this case is going to be the hundredths place, so the answer must be condensed to that location. Which brings us to the next issue. We have to decide, do we round or not? How do we determine if we round? We look to that last number, or our first insignificant digit, and we decide its relationship to 5. Is it bigger, equal to, or greater than or equal to 5? Which means we add 1 to the number in front, and our answer becomes 19.44, which is E. Questions? Straightforward? Or is this like, oh my God, I got to remember this? Okay, so far. Express, oh man, really? Express the exponential number 6.26 times 10 to the third as an ordinary number. Personally, I think it's a dumb question. Personally, I think that's a dumb question. But neither here nor there. How do we do that? How would I do it? Punch it into the calculator. And hence it being a dumb question, you'd end up with 6,260? Yeah. There you go. B. Okay.
So now I'll get 1 right?
Fair enough. Okay. Any questions about any of those shown so far? Okay. I need to do this. And I need to scroll. Man, 3 at a time. This is going to be exciting. Which of the following unit factors is derived from the relationship of days and years? Well, what is the relationship between days and years? 365 days is 1 year. I'm just going to write YR. So that is our mathematical expression of equals. What they're now listing out is the fraction version of it. So what we're looking at is 365 days per 1 year, or the reverse, 1 year over 365 days. You'll notice they gave through a whole bunch of other weird kind of conversions, but we're looking at C. Man, that is just obnoxious. Yet another one I should be covering up the microphone on. Okay, 1 year is 365 days. If a patient isn't, questions. So your unit factor is just that division symbol, or that division system. Okay, we're taking our, how do we convert two values, and we just put it into a fraction. 5, if a patient is injected with 0.5 liters of IV liquid, what is the volume in quarts? You notice this is an English metric conversion. Oh my God, but we didn't memorize it. We didn't give it to you. It's not on the front of the exam.
It tells you right there.
But it does tell you right in the question. Okay, so how do we set this up? I'm going to give you a hard time for that. How should you set this up? This needs to equal quarts. What are we given? 0.55 liters. Is there a conversion factor that allows me to go from liters to quarts? What is that conversion factor? What shows up in front of Q? 1. What shows up in front of liters? Okay. Let the units solve it for you. Figure out where all the numbers are supposed to go. Don't just start dropping numbers in. Oh, I just got to divide. Yeah, you had to divide in this one question. But the units or the numbers will change. So you can't just assume, oh, you always divide. 6. Oh, sorry, you want an answer on that? I don't have a calculator. 0.5 divided by 0.9. Yeah, it should be pretty good. Yeah. I agree with B as an answer. Okay. Rough approximative techniques on this one. What is 0.9 pretty darn close to? 1. So we're taking 0.5 and we're either multiplying or dividing by 1. So our answer should be pretty darn close to 0.5. Okay. So that means we can get rid of 1.89 and 0.946. Okay. So if you don't have a calculator, you can still approximate and eliminate answers. Okay. Next one, a penny is minted. I don't want to read it all. What is the mass of zinc in the coin? What do we want as an answer? Our grams of zinc. What are we given? We are told that we have a mass of our penny of 2.507 grams of the penny. So if we follow with our units, we want grams of our penny. That says penny. With grams of zinc on top. Do we have a conversion factor for that? If I give you 100 grams of pennies, how much gram, or what's your gram of zinc? 97.5. 97.5%, meaning out of 100. Okay, so we can swap our numbers and set that up. We go through and punch it into our calculator. We're going to again get something darn close to 2.5. What are we going to be, just under 2.5?
So 2.44.
There's that 2.38, which would make me nervous. I'd want to put it in the calculator. Is it 2.44?
Yes, right.
Hi. Yes.
Could I just do 0.975 times the mass?
Is that the same thing as we're doing right now?
Yeah.
Yeah. Okay. So if you want to convert the 97.5% into 0.95 or 975, that's fine. Your percent is now per 1. Okay, perfectly valid. Questions? Close that. Yay, 4 questions. Not that button. Physical quantity is expressed by the metric unit kilogram. What do grams measure? What physical quantity or unit would we use for length? Meters or lowercase m. Volume? Liters or capital L. Density? Grams per milliliter? None of the above? Good answer, I don't know. According to the metric system, 1 liter equals 1 times 10 to the second. This one's a little bit trickier on how you would go through and process this. So the problem is I know the answer. How do I avoid getting the answer without saying the answer? Right? Question over 1 liter. How can okay, well, we'll do it this way. Can I do it this way? Shoot. How can I do this without actually saying the answer? Did anybody got an idea on this?
It's none of the above. I think it's none of the above.
It's not none of the above.
It's not, well, then
What's the...
Well, your base is, right? You're starting with the base.
The base unit is liters, yeah.
You're moving it to decimal twice.
So what you're saying there is you're doing the King Henry lies to stupid dogs in the middle of the night statement. Yeah.
drinks chocolate milk.
I don't know. What does he do? King Henry drinks chocolate milk? Really? Is that it?
Drinking chocolate milk.
Whatever that is. Let's try it this way, actually. Here we go. I got it. Our unit, 10 to the second. Okay, our conversion factor, our power of 10, always affects the base unit. So this is 10 to the minus 2 liters equals what liters? What matched 10 to the minus 2? Centi. Okay, so that did kind of work. That is ultimately something you're responsible for. This one gets a little bit weird because the way we've memorized those prefixes is by the power of 10, and they've swapped the conversion on you. Okay, kind of makes sense? So beyond just telling you to memorize those common conversion factors, I don't have a better answer for that. Was that a hand, Pierre?
Yeah, so centiliters times 2, millimeter for base times 3.
So if we look at what those prefixes mean, centi is 10 to the minus 2 liters. Deci is 10 to the minus 1 liters. Kilo, sorry. 10 to the 3 liters. And milli, 10 to the minus 3 liters. So if you go back to the memory list, you'll notice that I have all 4 of those on the memory list.
We'll go lower than milli.
Could you go lower than milli? Yes.
Will the test go lower than milli?
I can't specifically answer that, short of telling you you should take a look at the memory list. Osmium is the most dense element. What is the mass of 10.0 centimeters cubed of the metal? What do we do? What are we trying to solve for? Solve for units? Quite accept that. Grams. Why'd you pick grams? The question doesn't actually say grams in it.
Mass, what is the mass? Mass is
Could be kilograms. All of your answer choices say grams. Okay. So I wasn't saying you were wrong. We just got to make sure you're finding where that correct information is. What are we starting with? I'm here in the 22.5. I'm okay with that. Why would you put 22.5 grams over centimeters cubed as opposed to 1 centimeter cubed over 22.5 grams? So what I'm asking is which one of these unit factors is more appropriate for solving this problem? Purple or red? Why the purple? We want grams where in the answer? In the numerator. Okay, that's why we leave it in that fashion. Okay, what do we need to multiply this by then? To multiply it by centimeters cubed. Do we have any centimeter cubed information?
Yep.
Yeah, we know it's 10.0. Centimeters cubed cancel out. And we could approach that sig fig question. This is why I said that sig figs isn't a big deal. Take a look at your answer choices. Are we even asking about sig figs?
Yep.
It is not relevant whatsoever. Okay? So you don't have to stress on the sig figs short of a sig fig question. Make sense?
Yeah.
Question 10. Liquid nitrogen boils at 196 degrees Celsius. What is the boiling point on the Kelvin scale? Negative 196 plus 273. And we should have a positive 77. What answers could you eliminate right away? All of the negative values. Why?
Calvin does go.
What?
Your positive number is bigger than your negative number.
So we can go through and do numerical comparisons, but our standard rule is that our lowest Kelvin value is 0. Okay, that's why we hit absolute 0. Just because we can scientifically do that in some other weird way to get less than 0, officially 0 is our bottom line. Okay. Questions? Okay. So the other thing I want to now kind of bring in here is you guys all seem to get these questions pretty easily. Should we be doing this in reverse order?
Sure.
Yeah, I think it is tougher. So hopefully nobody's watching the screen too carefully. '68. Apply the like dissolves like rule to predict which of the following liquids is not a good solvent for bromine. So the first thing that I would expect everybody in this class to do, because I am your instructor, would be to change this question. And you would change it to like forces dissolve like forces. What are the forces on bromine? How do we determine our forces?
Look at what's there.
What do you mean by look at what's there? Identify the bond. What type of bond do we have in Br2?
Non-polar covalent.
Bromine bound to bromine, we have a nonpolar covalent bond, which leads to what force? That takes us to our LDF, or London dispersion forces. If we go back to our rule, like forces dissolves like forces, and this is where it's extra obnoxious.
There's like 3 of them that
3 of them that have those same London dispersion forces. How can we choose between those answers?
guess it up.
Not a good solvent. Okay? So we are not looking for like forces and like forces. We are looking at opposite forces. What is the opposite force to London dispersion? What do we need to find? What is opposite of London dispersion forces? Go to your extreme case first. Ionic, followed by hydrogen bonding, followed by dipole-dipole. So we will start at our ionic force. How do we know we have an ionic force? Metal and a nonmetal. Do any of those compounds have a metal and a nonmetal? No. So ionic is not what we're looking for. The next one we would move to? Hydrogen bonding. How do we know we have hydrogen bonding? There's an H bound to oxygen, nitrogen, or fluorine. As long as that's there, we have a hydrogen bonding solvent, which means water is your answer. Make sense? Yeah. A lot of individual steps go through and determine what's happening with these molecular interactions. You got to recognize the formula, determine the bonds, then look at the forces, and then you're evaluating the definition of whatever you're looking for. In this case, it's solubility. How do we know something is soluble? Okay. Other examples will be melting points or boiling points or vapor pressure. So you're applying the same idea, but you're now using a slightly different definition for your answer. Okay. And then, as always, watch out for the knots. Okay. The knots will mess with you. Questions on that one? Okay. Is that a question? Not at me?
What?
I'll take that as a nod at me.
No.
67. What is the molarity of a sucrose solution that contains 10.0 grams, that big long thing, dissolved in 100 milliliters of solution? What are they asking for? Molarity. Molarity is a horrible thing to determine. What is molarity? It is moles over liters. Okay. Do we know either of those values? Yes and no. It's kind of a little bit weird in that case. For those of you that said yes, that we know one of those values, what are you saying you knew? Okay. What you went through and did is figured out that our liters, was that 100? Milliliters times a quick conversion factor gets us to our liter unit. What's our conversion factor? 10 to the negative 3 over 1 gets us our liter value, which is 0.100 liters if we want to be nitpicky on our sig figs. Do we have to worry about sig figs? Looks like we're not going to have to worry about it. So we now know the liters for this. What do we need to figure out? We need to figure out our moles. Quickly running out of space. Let's just erase that question. We weren't using that anyway. How do we figure out our moles? What information do we have? We have 10.0 grams of our compound. We are trying to convert grams into moles. Where would we typically find the gram to mole conversion? On the periodic table. That's a lot of extra work. Sometimes they give it to you. They give you the gram per mole value. They're telling you 342.34 grams is 1 mole. So what do we have to do? What do you put in front of moles? What do you put in front of grams? Whatever that number was. 24. Punch that into our calculator. We got our moles. We divide that by the 0.1, and we have our answer. Which you guys should probably give me. Was that 0.342? Oh, okay. Well, 292 grams. Molar. All right. Questions? Okay. Hey, look at that. What are we doing? 66. What is that asking about? Oh, look at that. The exact same thing again. Apply the like dissolves like rule to predict which of the following liquids is miscible with water. Okay? So immediately, like forces dissolves like Forces. Decided to be a little bit tricky here.
D. Sorry.
They brought in this weird word miscible. What did miscible mean?
Soluble.
That they dissolve, that it's soluble. Okay, so this is not a not question, just a straightforward one. First thing we should figure out is what is going on with water. We have H2O. You might have jumped already to your forces. Your forces say H bonding. What do we need to find then?
Something that H bonds.
We're looking for something with hydrogen bonding. Which of our answer choices has hydrogen bonding?
D.
D, glycerin. Okay. Questions about that? We just did that one very, very, very fast. Okay. Yeast and sugar are added to champagne to give the sparkle of carbonation. You guys laughed when I said sparkling. Under what conditions is the solubility of carbon dioxide gas the greatest? So what are we trying to do? We got a container. Here's our champagne. Here's CO2. What are we trying to do with this? We're trying to push the CO2 into the liquid. How do we do that? High pressure. Okay, so that means, nice of them to change the order on these. Pressure is a factor, so C can be eliminated. D can be eliminated because it says low pressure. Okay, we now have A, B, and C. All of them are asking about temperature. Does temperature affect this?
Yes.
Yeah. What do we want our temperature to be? We want our temperature to be very low. We're trying to take something that has lots of energy moving around as a gas, and we're trying to force it into a tiny little space. Okay? Which means we want low temperatures. Remember, take that bottle of champagne and put it in your car during the summer. It's going to explode. Why? Well, it depends on your champagne. I guess it depends on your car, too. You're increasing the temperature of the liquid, which now is causing all of that CO2 that was dissolved and turning it into a gas. Eventually, it blows open the champagne container. High temperature reduces solubility. We're trying to increase solubility.
Is that why they put it in ice besides it being chilled?
Have you ever had warm champagne?
No, don't.
It tastes a lot better when it's cold. So we want low temperature, high pressure. That's not true. Whiskey needs a little warmth.
Scotch.
Based only on, questions on that one. Okay. Based only on intermolecular attraction. Hey, look at that, another cool question. Intermolecular attraction, also known as forces. Predict which of the following liquids has the highest vapor pressure. Oof. What is vapor pressure? This is one we just talked about, so it's okay if you don't remember it. What is vapor pressure?
B. Looking for lowest, right?
Still looking for that answer.
Highest.
What is vapor pressure?
Pressure exerted by gaseous vapor upon liquid.
So we are looking at the pressure exerted from the gas that came from a liquid. Okay, for it to get into the gas phase, what has to happen? Sort of.
Forces have to break.
We have to break all of the forces that are connecting those molecules together to keep them a liquid. So we have to break those forces to get them up into the gas phase. Once they're in the gas phase, they can now have a high vapor pressure. They can push against the container more. Okay? So what kind of force do we want for our liquid? A really strong force or a really weak force? We want our liquid to go into the gas phase. Once it's in the gas phase, we now have vapor pressure. If it stays a liquid, no vapor pressure. We want the weakest possible force. The weaker that force is, the more likely we will transition into the gas phase, the more likely we will have, or we'll now have more particles in our gaseous phase. More particles means more pressure. So we are now looking for the weakest force. What is our weakest force? London dispersion forces. None of those list the forces. How do we get London dispersion forces?
Same bonds in an HC.
Yes, that's the definition. We're looking at same to same
With HC.
and just H to C, which would work for this question. Ultimately, by defining that, you're providing the definition for what type of bond? What type of bond matches the definition, same to same, or hydrogen to carbon? What'd you say? Thank you. Non-polar covalent. So now that we've got what we're looking for, we can go through and look at the question. I see O and O. What does that mean? It means polar covalent bonds. That's not the non-polar covalent. That doesn't fit my same to same and whoops, I guess I should highlight the H again. Okay. Or the C to H. We move to the next one. I see C to H, C to H, C to H, C all the way through. Hey, that's starting to look like a pretty good answer. Next one. O to C. Next one. C to Cl. Last one. C to S. The only one that the best one that represents my current definition is B. I don't care if you got the answer right, you need to explain it. Okay. That's the game, you have to explain. The game is to explain. It kind of rhymed. Oh man, bunch of calculations. Hey, I got another one. 61. So, 63. Percentage of water in borax. Okay. This is kind of one of my least favorite things when we reference percentage because we're always vague about it. They're really saying the percentage by mass of water in borax. So how do we figure this out? What we will go through and do is assume that we have 1 mole of this species. Why 1 mole? Why is it easy? We don't have to multiply something by the atomic weight, so we can just figure out the atomic weights. Yeah, that does work. And not officially our atomic weights, but instead our molar mass. Okay, because we're using 1 mole. So what is the molar mass of sodium? 22.99. There are 2 of them, so I have to multiply that by 2. What is the molar mass for boron? What do I have to do? Multiply by 4. Oxygen. What do I multiply by? Why'd you do 7? I agree, you should be doing 7 in this case. Why do 7? No. You're telling me there's no other oxygens in this formula? That's coming from our water. So depending on how we want to break up our calculation, we need to know the mass of oxygen all the way through the whole formula, but we'll have to separate the oxygen that came from the water in our calculation. So if we split it out all right away, that makes it a little bit easier. The mass of our hydrogen, 1.01. How many hydrogens?
20.
Why 20?
There's a 10.
We have a 2 and a 10. Oxygen, 16. How many oxygens? Why 10? The 10 applies to everything after it. What we can now go through and do is figure out the mass coming from just the water. Somebody handy with the calculator? 180? Yeah, I just saw that. Roughly 180. So this is our grams of H2O. And now we need to divide this by the grams of our borax. What is the mass of borax? So this is where I want to check. Where'd you get the 201.2? Is that just this number?
No, 3.8.
Okay, that's what I was looking for. If we take a look, sodium plus boron plus oxygen from our sodium Na2B4O7, that is our 201.2. Okay. Should I use that number as my mass of borax? No. The mass of borax includes water. So what I have to do is add both the 201.2 and the 180 to get me, what did you say it was? 381.2, something like that. Huh?
I got 379.9.
379.9. So somewhere or another we made a addition mistake within that. We can then divide those numbers and we should end up with our final percentage. Questions on that? So those exact numbers, I don't know if the exact numbers are right, so don't quote me on those. Okay, but we should be getting something darn close. No questions? Okay. Which of the following properties is a general characteristic of solids? Probably the only question I would not write anything for. And I would also probably skip. Any ideas why I might skip this question? Nope. Actually, I don't know that. It could be on the test. This question requires that I read every single statement. I have 5 answer choices. Of those 5 answer choices, 4 of them are wrong. I'm spending most of my time reading wrong answers. I would rather move to a question that I know answers are correct for. Okay? It's just a time-saving technique, and that is it. Okay?
Forget about the question and not answering.
What's that?
I would end up forgetting about the question and not answering.
So you have to come up with techniques that work for you. You will probably not have a time crunch on this exam, but that is proper test-taking strategy. Move on when you can. So which of the following properties is a general characteristic of solids? Rigid shape, variable volume. Solids always have crystalline structures. Solids compress and expand significantly. A substance is usually less dense as a solid than a liquid.
Oh, crap. What?
I always hate this kind of question too, just raw memorization. Solids always have a crystalline structure. That's not going to be true. Okay, so what I would probably go through and do is eliminate answers, and then I would get really frustrated with the question. Solids compress and expand significantly. No. A substance is usually less dense as a solid than as a liquid. Okay, it's typically the opposite. And then none of the above. And as soon as I saw none of the above, I would absolutely skip it. Okay? Because now I have to know that one of those is true. Rigid shape and a variable volume.
I think so.
The volume shouldn't be variable for an individual substance.
So it
It
is.
should have the same volume. So that sounds like it would be E, none of the above. That is one that for sure would throw me for a loop too. The whole rigid shape and volume thing is, why do I care? Okay. What is the strongest intermolecular force in a liquid having molecules with HN bonds? HN, go through our forces. If we have a hydrogen bound to nitrogen, oxygen, or fluorine, we have hydrogen bonding, which is a force. What type of bond would we have? It's not covalent. No, it's polar covalent. Let's say both of those answer choices were given to you. What's your answer? Why hydrogen bonding?
Because it said forces, not.
Said forces, not bond. Polar covalent is a bond. Hydrogen bonding is a force. Our answer in this case is hydrogen bonds, which I find irritating. But that's what we put down as our answer. It's not a bond. Why is it called hydrogen bonds? Because it's a test probably written by people that don't do organic chemistry. No, I don't have a superiority complex. I just acknowledge that. That didn't go over very well. Okay, let's try that again. What is the molecular shape of water? How do we figure out molecular shapes?
Draw this structure, Lewis dot structure.
Lewis dot structure. So what do we do as our first step? Nope.
Pick a center.
Nope. First step. Count the valence electrons. How many valence electrons does oxygen have? 6. How many valence electrons does hydrogen have?
1.
How many hydrogens are there? Which means I have a total of 8 electrons that need to go into my structure. How do we figure out the valence electrons? Is that what you guys are asking?
No.
Oh. Yes? No, that's fine. How do we figure out the valence electrons? It is on the periodic table, but how? That information is kind of buried in there.
The top little row.
So we can look at the Roman numerals across the top. Those specify our valence electrons. The other thing that we can do is our valence electrons are our highest energy shell. Where's our highest energy shell on our periodic table? I know that sounds kind of weird. Nope, that's not the shell. Lowest. The lower it is, the higher the energy. Okay? On our periodic table, it's how we've organized it. So our valence shell for, I already forgot our element, oxygen. Okay? We would move to the second row. That is its highest energy shell. How many electrons does it take to get from the left side to oxygen? So to go from the left side that is not on the column to get to lithium, how many electrons do we have to add? 1. How do we move to beryllium? Add another one. 2. Boron. 3. I already forgot the next element. Carbon. 4. Nitrogen. 5. Oxygen. 6. Right. That gets us our valence count just as easily as the Roman numerals do, or the column number. Okay. Now what do we do once we've got our valence electrons, or our total electrons?
Pick a center.
We need to pick a center atom. The center atom is typically the least electronegative, but it must bridge, which means oxygen is our center atom. We'll scatter the other elements around it. Now what do we do?
Don't do it like that. Do the other way.
There's a reason I'm doing it like this, because the odds that you do it this way are very high. Add dots representing electrons. Where do we put our electrons first? Where do we put the electrons? Almost. Not the least electronegative. We put the electrons around the most electronegative, which in this case happens to be oxygen, which also happens to be the center atom. It does not have to be the center atom. We've got our 8 electrons in there. Once we've got our 8, we can convert pairs of electrons between atoms into bonds. Okay? And we now have our Lewis structure. Once we've satisfied octets, we've got octets for water. How do we then determine the molecular shape? Okay, and the biggest reason why I drew it like this is 9 times out of 10, this is how students draw the formulas. You put the atoms as far away from each other as possible. If we just look at this formula, we might jump to what shape? Linear. As you've already discovered, it is not linear. We need to know why it is not linear. What are we looking at?
I was going to say, why don't we put them like that again?
Typically, you will organize your atoms to get as far away from each other as possible. It has nothing to do with the actual structure. It has nothing to do with proper way to do Lewis structures. It's just, you just naturally do that. Okay? Think about when you, there was a bad example, walk onto a bus, okay, or some kind of mass transit. Do you go to the seat that's right next to somebody that you don't know, or do you go find an empty seat where there's nobody nearby? You go find the really empty seat. Okay? You're trying to get as much space as possible. So when we draw out our structures, we tend to do that already. We have to be careful when we go through and do that and realize that does not have anything to do with shape. How do we determine shape? We have to look at the electron groups around our central atom. What are the electron groups around oxygen? How many groups of electrons are there? 4 groups of electrons, which means in electron geometry, tetrahedral. How do we get to our molecular geometry? Our bonding versus non-bonding. We have 2 bonding, 2 non-bonding. That means the bent shape is our correct answer. Cannot emphasize this enough when you go through and do the practice exam. You will not see these same questions. You have to understand how we get to the answers, not, oh yeah, it's just bent, because I know water's bent. If I change it to H2S, how many of you have worked with H2S before? Huh. What's its shape? It's the same thing. Yeah, it's bent. Okay. How would you know that? You have to go through and draw out your Lewis structures to recognize those patterns. Okay. And it's looking at all the electron geometries all the way through. Question? So let's move to 59. Electron pair geometry for phosphine. Okay. Is phosphine bent? Does anybody actually know that one off the top of your head? Probably have to solve it. So how do we solve it? To draw the Lewis structure, phosphorus comes in with 5. Hydrogen comes in with 1, but there's 3 of them. Our total is 8. Right? Sorry, someone said what? Made me nervous. I did the math wrong. What's our center atom? Phosphorus. Scatter our other atoms around it. What do we do now? Pairs of electrons until we reach 8. Why reaching 8? Not octet rule. That's how many electrons we have. Okay. You can only add electrons up to your total. The total in this case happens to be 8, which also happens to be the octet. Okay. That's not necessarily always going to be true. Okay. You add electrons around an atom around your atoms until you satisfy all of your valence electrons. Right? Any place that we have a pair of electrons between atoms, we can turn into a bond. How many groups of electrons are around the phosphorus? We have 4, which means tetrahedral. Our answer is trigonal pyramidal. No, it's tetrahedral. Sorry. I apologize. I shouldn't have done that.
That's molecular, right? Trigonal pyramidal.
What is the molecular geometry? That is trigonal pyramidal, because we have 1 bond or 3 bonding and 1 non-bonding, which gets us to the trigonal pyramidal geometry. Okay? Questions? Do we need to do 58? Just because we...
Yes.
Oh, okay. 58. No, we didn't just do 58. CH4, where do we start? Valence electrons for carbon. 4 valence electrons for hydrogen. Times 4, which gets us 8. Central atom. Carbon. Scatter our other atoms around it. Pairs of electrons. Any place that we have a pair of electrons, we can turn into a bond. Or just erase all the atoms, because that's what I feel like doing. Molecular shape. Okay, we'd start with our electron geometry, tetrahedral. We can move to our molecular shape. Still tetrahedral, because there aren't any non-bonding pairs of electrons. And we'd have tetrahedral as our answer again. Questions? Yes? It's the electron pair geometry in 59. Electron pair geometry does not distinguish between bonding and non-bonding, so it stays tetrahedral. If we'd asked for the molecular shape, yes, trigonal pyramidal. We did not ask for that, so you got to be careful on what the question asks for. Questions?
57 is
Okay, so I'm going to clear all that out of the way because it's a mess. According to the general trends in the periodic table, which of the following is the most electronegative element? Fluorine. I would argue that this has nothing to do with general trends. Why?
Because it's the most electronegative.
Fluorine's the most electronegative, period. Okay. Our trend says the upper right is the most electronegative. What is the upper right? Helium. Okay. So it's not according to the trends, it's according to what is the most electronegative. Okay. Questions? Come on, mouse. Oh, even better. Even more Lewis structures. Okay. Yeah, good thing you did that lab.
I actually did the lab.
Say thanks to me. I pushed you guys and made you keep doing
My
it.
teacher did the lab.
So, 56. What do we do? Count electrons. Carbon has 4. Oxygen has 6. There are 3 oxygens. Why do we have to add 2 more? Yeah, give me a sec. It just lost connection. Carbon comes in with 4. Oxygen comes in with 6. There's 3 of them. To have a negative 2 charge, we have to add 2 more electrons, which gives us a total of, is it 24? Okay. 24. What do we do now?
Make the least stock structure.
So we start by doing least electronegative that can bridge in the middle, which is carbon. What do we do now? Now what do we do? Why do we put the electron pairs around the oxygen? Oxygen is the most electronegative. When do we stop putting electrons around oxygen?
Once you reach your octane.
Okay, just checking. Once we got 8 electrons, come on, around an individual atom, we can then move on to the next one. And our next one. And we would have covered how many electrons? 24. So we've reached our total electrons. We stop adding electrons. Look for pairs. Draw in our bonds. And now we have to evaluate what it says. How many bonds show up in our structure? Almost there. According to our structure, if this is where we finish, we would say 3, and we'd be wrong. What's the weight?
Carbon's octane is satisfied.
We have not satisfied the octet on carbon. Okay. So before we can answer the question, we have to achieve our final structure, our final correct Lewis structure, which means every atom needs to have its octet. That means we will move a pair of electrons from one of the oxygens in to make a double bond. Now that we have that pair of electrons present, we can now evaluate the question, or what was asked of us. Is resonance relevant? Not really, because they aren't asking you, is there resonance? They're just saying how many bonds are present. Right? So in this case, what do we have? 2 single bonds and 1 double bond. There's our answer as answer choice B. Questions on that? Okay. 55. Should pause the video. We total all our electrons. We got 18 again. Start putting electrons around our oxygen first. Why around the oxygen? more electronegative. We would now have how many electrons? 16. I need to have 18. Where do I put the last 2 electrons? On the selenium. Now I can go through, convert pairs of electrons between atoms into bonds. Check to verify octets. Does my oxygen have an octet?
Yes.
Yes, both of them do. Does the selenium?
No.
No. What do I have to do?
Fix it.
I have to fix it by moving a pair of electrons in. I now have my correct Lewis structure, which means my answer is 1 single, 1 double. Okay. This is why you count your electrons. Okay. Try to avoid skipping steps. You've got lots of time, so you don't need to worry about skipping steps. Questions on any of those? Potassium metal, yeah, why not? Let's go ahead. Potassium metal and fluorine gas, oh, there's another one I don't like. React to form potassium fluoride. Which of the following statements is true? Yet another one that I would immediately skip because 4 of the answers are wrong. Okay? I want to avoid spending my time looking at wrong answers. Okay? So far, I've only skipped 2 questions. It's not that bad. Just saying.
Technically, 4 of them are wrong.
True, but I have work to give me an answer that I can now eliminate answers. Whereas here, I actually have to read the text for all of them. Okay. So, we are forming potassium fluoride. I might go through and write out that I have potassium solid plus fluorine gas to give me potassium fluoride. Okay. That might be something I'd be willing to go through and do. It just kind of depends on what the question was. So then I would read ahead. It says potassium ions lose electrons, fluorine atoms gain electrons. So what I'm talking about is what's actually happening to each of those atoms as they pass through this reaction. Okay. So what I'm concerned about is what happened to potassium, what happened to fluorine to look like KF. Okay. I was having a conversation with someone earlier about redox not showing up. This is actually a redox one. We write out the equation. It actually helps us out to answer this. Oh, you're right. Thank you. So, what happens to the potassium? What was that?
So it loses electrons.
How do you know it loses electrons?
It's in group 1, and it wants to give it to fluorine.
So you're saying in KF, potassium has a +1 charge. I don't necessarily have a problem with that. What I have a problem with is why did it not start with a +1? How do you know that wasn't the case?
No, wasn't specified.
Upper right-hand corner for that formula for potassium, is there a charge written? No, it's potassium metal. It's in its elemental state. Its charge is 0. What is the charge for the fluorine?
0.
What is the charge for the fluoride?
0.
-1. Okay. What happened to the potassium to go from potassium 0 to potassium +1? It lost electrons. What happened to the fluorine? Gained electrons. So A starts to sound reasonable. Okay. Potassium atom is smaller in radius than potassium ion. Yeah, I really don't like this question. This question goes all over the place. You're looking at reactions. You're looking at atomic sizes. There's a lot of different things being asked in these kind of true-false questions. So it's one you got to be careful with. Potassium atom is smaller in radius than the potassium ion. Okay. What happened to potassium? It lost electrons, which means what happened to its size? It shrunk. Potassium ion is smaller than potassium atom. Is this statement true? Potassium atom is smaller than potassium ion? No, that is not true. Okay, the potassium ion is smaller because it lost an electron. It's now down in that 3rd energy level as opposed to the 4th, so it gets smaller. The fluorine atom is larger in radius than the fluoride ion. What happened to the fluorine atom? It gained an electron, which means it should be getting bigger. What does this say? The opposite of that, which means not true. With all of that, I would also then eliminate the all of the above. Potassium ion and fluoride bond by sharing electrons. Ooh, what does that mean? Potassium ion and fluoride bond by sharing electrons. Tricky.
That's not true. It's an ionic bond. Don't share it.
It's an ionic bond. By definition, in an ionic bond, the electrons are not shared. It is a transfer of electrons. That one is not true. Your potassium atoms lose electrons and your fluorine atoms gain electrons is your answer. Okay. Questions on that? Really, no questions? No, okay. Starting with 0.657 grams of lead-2 nitrate, a student collects 0.925 grams of precipitate. If the calculated mass of precipitate is 0.914 grams, what is the percent yield? Good place to start. Your percent yield is your actual over theoretical. All right, that's how I've been telling you about it. We've changed the terms around a little bit, officially times 100%. It is also known as the actual over calculated. Because your theoretical yield must be calculated. So given that information, what can we go through and do now? What was our actual yield? 0.925 grams. What was our calculated yield? 0.914 grams, which gives us a number greater than 100%, which then means everybody goes, oh, I can't get bigger than 100%. I must have put the numbers in the calculator wrong, and recalculates the other way and gets 98.8%, which is also wrong. Okay. You should not get above 100%. That does not mean you won't get above 100%. Okay. So it's following the formula of how you calculate percent yield. It is always actual over theoretical or actual over calculated. It is 101%. You should never get that. Is that what this student got, though? Yes. So you can't change the results. If your results tell you you're over 100%, then you're over 100%. Period. Okay. And yeah, that would then be your conclusion. Something went wrong. All right. 52. What mass of aluminum must react to release 1 gram of hydrogen gas? This is a really long question, but we'll solve this as our last one. So what units are we looking for our answer? Not true. Yes. Finish that. Grams of aluminum. What did we start with? 1 gram of hydrogen gas. What's our formula for hydrogen gas? H2. Let's come back to that statement in just a second here. We're trying to convert grams of hydrogen into grams of aluminum. Is that a direct conversion? No. What can we convert the grams of H2 to? Moles of hydrogen. How do we do that conversion? Molar mass, which is found on the periodic table. What is our molar mass? 2 grams per 1 mole of H2, which comes out to be a half mole, not 1. So you got to be careful, write down your work. Ideally now I would try and go from moles of H2 into grams of aluminum. I can't do that, but I can go into moles of aluminum using the what equation? The balanced equation. Is the equation balanced?
No.
No, so what do we have to do?
Balance it.
Balance it. Where do you want to start?
HCl.
What are you starting with? HCl?
Yes. Put a 3.
Which one? Put a 3? Okay, so it sounds like we're balancing the aluminum. So, or sorry, our chlorine. Is our chlorine balanced?
Yes.
Yes. Is our aluminum balanced? Really?
Yes.
The aluminum is balanced. Is our hydrogen balanced? No. We would need 3 halves. Hey, this question looks really familiar.
Times everything about 2. 6, 2, 6, 2, 3.
We now have our balanced equation. What number shows up in front of moles of aluminum?
2.
What number shows up in front of moles of hydrogen? We're now in moles of aluminum. How do we get moles of aluminum into grams? The molar mass, which is found on the periodic table. Our aluminum, was it 26.98 grams per 1 mole? Punch it into the calculator, we now have an answer. Questions? Okay. We are officially done. I have no problems continuing for those